In section 3.3, I'm going to discuss drag and terminal velocity. Drag is the force of air resistance that's exerted on an object when air and an object move past each other. Usually, we'll talk about an object that moves through stationary air. So, in this case, where we have a skydiver falling downwards, the skydiver's velocity is down, and so the drag force will be exerted upwards on our skydiver. There are three factors that affect uh, the effect of air resistance. The greater the mass of an object, the smaller effect that drag has on an object. Now, the effect that I'm really talking about is the acceleration of the object. And we'll learn in a few units that this is inversely proportional to an object's mass, meaning the heavier the object is, the smaller the effect of a force acting on it. Speed also affects drag. The greater the speed, the more effect that drag has. And this is because the drag force is proportional to the speed squared. So if we have an object that's moving twice as fast, the force of drag on it is 4 times as large. Also, the cross-sectional area, and I'll explain what I mean by that in the next slide. The more area that runs into the air, the more effect that air has. Again, this is because the drag force is proportional to the cross-sectional area. The more area that runs into the air, the greater the drag force. Now, when these three factors are very small, then the effective air resistance is very small. And if it's small enough that we can ignore it, we refer to it as negligible. And when this happens, our free fall models are indistinguishable on real world models where we have objects that are moving through air. So only when the effect of air resistance is negligible can we say that our free fall models do a good enough job to model real world objects moving through air. Okay, so everybody's played this game, right? Where you stick your hand out the window of a moving car. And we all know that there is less drag pushing your hand backwards when you put your hand like this than when you put it like this. There's more drag over here. That force that pushes your hand backwards, that's drag. And the reason for it is that drag is proportional to the cross-sectional area. And you can see pretty easily what I mean by that. Here is the area of your hand that's running into the air when you hold your hand sort of sideways. It's only that leading edge of your hand that's running into the air, where over here it's your entire palm that's running into the air, and the area of your palm is greater than the area of the front of your hand. That's why you feel more drag when you put your hand like this. In this example, we want to know under what conditions is it appropriate to say that the effect of drag under what conditions is it appropriate to say that the effect of drag is negligible? This is an important question because when drag or air resistance is negligible, then our free fall models can accurately describe real world situations. So there's three factors that affect the effect of air resistance. And so when those factors are very small, then we can say that air resistance or drag is negligible. So objects with a small cross-sectional area have a small drag force and therefore a small effect from drag force. So there's two kinds of objects that have a small cross-sectional area. We have objects that are designed so that they are aerodynamic. Aerodynamic objects are designed so that when they move through the air, the way that they're moving through the air doesn't have a big area, and so then aerodynamic objects like an arrow or a dart, they have a small cross-sectional area. The other kind of object is just a small object. A small object, just because of their size, tend to have a small area. The the other factor that affects the effect of air resistance is the mass of an object. So when there is more mass, there is a smaller effect. So heavy objects tend to have a very small effect from air resistance. And it's important to point out that small objects that are also heavy are dense. So objects with a large density, such as like maybe a lead bullet, they make bullets out of lead because they're both heavy and they're small. They're dense, and that's why we would make them out of that. The third case is speed. So at low speeds, air resistance doesn't really play much of an effect. And so the faster that we go, the further our free fall equations are going to get in predicting and modeling the motion of objects in the real world. So I gave several examples. Arrows are a good example. Dense objects like a bullet would be a good example, or just everyday objects that are moving at low speeds. So a counterexample: when would this? When are all of these factors not in play? Well, a good counterexample that I always think about is a beach ball. All right, if you've ever played with a beach ball, the drag force plays a big role in this, and the motion of a beach ball will not be the same as the motion of, say, a baseball. The baseball isn't affected by the drag force very much, where a beach ball is. Okay, so when we're describing a falling object with drag, if drag is not negligible, then we cannot apply our free fall equations. Our free fall models are not accurate. The magnitude of acceleration won't be g, it'll be something else. Also, it is not going to have a uniform acceleration. The acceleration is going to change as the object's velocity changes. And it's sort of like a feedback loop. The acceleration depends on the affects the velocity, but then the velocity affects the drag. But then the drag affects the total unbalanced force acting on an object, which in turn affects the acceleration. And so there's this feedback loop that continues. One thing affects the other. And so the acceleration and the velocity in turn kind of affect each other. So we can't use the equations, but we can talk about what the motion looks like. Okay, so there's this idea called terminal velocity. Terminal velocity is the speed of an object when there is no acceleration. Okay, so if you drop an object, okay, so here's an object and we're going to drop it from rest. Initially, the only force acting on it is gravity. All right, because it's at rest. There's no drag force because it's not moving through the air yet. And so initially it is in free fall because the only force acting on it is gravity. So when we drop it, it will start to speed up and its graph will, its speed will increase, and the slope of this graph, remember the slope is the acceleration, this will be approximately g when it starts. But as it starts speeding up, then there's going to be a drag force. And that drag force is going to get bigger and bigger as it gets faster, right? The drag force is proportional to the speed squared. So as the drag force gets bigger, the total force, and when you find the total force, you have to add these two, right? And there's a bigger force down than there is up, so there's an acceleration down. But as the drag force gets bigger, the total force, the unbalanced total force, gets smaller, and so the acceleration will get smaller and smaller. And eventually the acceleration is going to drop to zero. So that means the slope is going to approach zero. And what that looks like on this graph is something like this, where the speed approaches some terminal velocity where the object is falling down, but it is no longer accelerating. It's no longer accelerating because when the velocity is terminal, the force of gravity acting downwards is balanced by the drag force. And when the forces are in balance, the acceleration is zero. And that's where the slope becomes zero.